So today we will talk about the second case for inverse kinematics analysis, which is a manipulator that does not have a spherical wrist. For this type of manipulators, actually there could be different methods for different manipulator structure. I would like to use the SCARA manipulator to show that how we're gonna do the analysis from the scratch. Means we see a manipulator and we know nothing, and we don't know the DH conventions and we know nothing. How we're gonna do that step by step. So if we want to do that, so first of all, let me show a video of SCARA manipulator and why we talk about it, because it's very commonly used in the industry. Okay, so I will stop here. So from this video, we can see that the SCARA robotics are pretty easy, right? It's compared to other manipulator, and this robotics, it has two revolute joints, which is one is here and one is here, and then there is a prismatic joint right here. So it can do a 360 degree of rotation. And also here we have a prismatic joint, so which means it can do the up and down, and so since it's simple and relatively low cost and stable, so this robotic manipulator is widely used in medical and also industrial robotics. Okay, so to do, say for example, now we know nothing about this SCARA manipulator. So now I would like to start to do the analysis from scratch. Okay, and then we go back to, first of all, we need to use robotic convention to generate the coordinates. We draw the joints and then we number the joints, and we number the coordinates of each joint, and then we start to have this diagram, right? This diagram. Okay, and for the SCARA manipulator, from the video we can see that, okay, so here we have a revolute joint, and here we have a revolute joint, and right here this is a prismatic joint, so that the end tooling can do up and down. And normally in the this kind of the tooling thing, and there is another revolute joint, and this revolute joint add the end effector, which is right here. Okay, so this diagram aligns with the real SCARA manipulator and we just saw from the video. And also the photo that I posted for the assignment, and that one was a medical SCARA manipulator. And so from the video we can see that, and the whole thing can do a full rotation. Okay, now based on the robotic convention, and we define, okay, here we have joint 1, 2, 3, 4, so we have 4 joints for the SCARA manipulator. And then we number the coordinates for joint 1, and we name as frame 0, right? And we have learned that. Okay, so here we have joint 1, so we have frame 0 and frame 1, frame 2, and frame 3. Okay, and then we add a frame 4, and frame 4 is for the end effector, which we now, I guess we're familiar with that, right? Okay, so now once we want to do the analysis from scratch, and the first step is we start with forward kinematics. Okay, and from forward kinematics, what is that? It means we use DH conventions. And also in our final exam, we will have a question like this, so that we give the diagram, and you need to generate the forward kinematics by DH conventions. Means you need to calculate, and you need to find 4 parameters for each transformation, and then you need to calculate the t and 0, and after you find the forward kinematics, and then we need to calculate the inverse kinematics based on the matrix we have. So today I'm going to show from the beginning to the end using this example. Okay, and so for forward kinematics for the SCARA manipulator, I think that's easy right now. And so if we would use DH convention, so first of all, we need to write down the 4 parameters, which are A1, AI, alpha I, DI, and theta I, right? And we write as 1, 2, 3, and so for 1, that is 0 to frame 0 to frame 1, and this is from 1 to frame 2, and 3 means from frame 2 to frame 3. Okay, and now we start to find the first row. And so what is AI? AI means on XI axis, the distance from Z0 to Z1. Okay, so on the X1 axis, which is right here, my Z0 is here, my Z1 is here, and so this is my AI. Okay, and here normally we need to do the analysis from the real manipulator system, so that we find what is, if there is a geometry, or it's just like we draw that there, but there is no geometry. So for example, a spherical wrist, although we draw 3 revolute joints, but it means there's no geometry, right? But although we draw 3 revolute joints like this. Okay, and so for a manipulator analysis, normally we need to go back to take a look at the real manipulator and see what are the real geometries. And as if it is in the exam or we do questions, and we will directly tell you that, okay, so here that there is a length and there is no length, or this length is 0, for example. Okay, so don't worry about that. And in our final exam and in our questions, we will tell you, okay? So now we tell that this is a 1 from here to here. It's like in the video, and imagine here we have the base, right? Here we have the base, and here we have a joint so that we can move. Okay, and from here to the prismatic joint, and we name the length of the link, which is A2. And from here to here, and say there should be a offset. There should be an offset, but normally we can name it as D1, but D1 is actually a offset. So to be accurate, there should be an D1, and now I assume D1 equals to 0. Okay, so I assume it's perfect and there's no offset. Okay, so D1 equals to 0 in this case, and this is different from your homework. So in your homework, we assume there is a D1, okay? So then we start to put in these numbers, okay? So here we have A1, because A1 is the distance from Z0 to Z1. And what about alpha I? Alpha I means the rotation from Z0 to Z1, and seems like they're parallel, so that is 0. Here we should have D1 here, but in this case we assume D1 equals to 0, so we give it 0. And the first joint is a revolute joint, and Z0 is my rotating angle. So here I have my theta 1 I mark as star because that is the joint variable. Okay, and the second row, we need to do the analysis of 1 to 2, okay? So which is 1 to 2, the frame 1 to frame 2, okay? And then what about AI? AI means on x2 axis, which is here, the distance between z1 and z2, okay? So we have a 2 here. And my alpha I means the rotation from z1 to z2, okay? So here I have my z1 and here I have my z2, and they're opposite. Opposite means my alpha is 180. And let's see if it is positive or negative. Alpha I means the rotation from z1 to z2 around x2 axis. So let's see what is the sign of that. So again, we use right hand rule, and if you have your right hand right here, and then they're going to be my thumb, okay, and here are the rest of 4 fingers. So it means if we rotate in this direction, that is positive. So we have 180. And DI is, in this case, it means on the x2 axis, it means on the x1 axis, the distance between x1 and x2, okay? And seems like they projected to the same point, so that is 0. And theta I means the rotation angle, which is in this case is the joint variable, okay? So that is theta 2 star. So the next one is from frame 2 to frame 3, and so here we have frame 2 and frame and this is a prismatic joint, okay? So if it is a prismatic joint and D3 is along Z2 axis, so it means that I have my D3 right here, and D3 is the joint variable, so I mark it as a star, and it is changing, right? Okay, it's changing. Okay, and then we do A1. A1 means on x and 3 axes, what is the distance between Z2 and Z3, okay? Z2 and Z3, okay? So these two frames, they're parallel to each other. So we have 0, 0, and 0, because these two are parallel, and the only difference is caused by this joint variable, which is along Z2 axis. Okay, and we also need to do the transformation from the last joint, which is joint 4, to the end effector, okay? So it means it's from frame 3 to frame 2, 3 to frame 4, okay? So it's 3 to 4. And again, the frame 4 is for the end effector, okay? Okay, and then let's see. Okay, so these two frames, they are also parallel. So we have 0, 0, and 0. And there is a distance, and this distance, let me call it D4, because D4 is the length of, from D4 means the distance between the joint to the end effector, okay, to the center of the end effector, okay, so that is D4. And again, right here, there is a revolute, so there is a revolute, this is a revolute joint, so that is theta 4 star, okay, means the joint variable. Okay, so then we start to write the matrices, okay. AI, again, we need to check the AI, and we plug in these real numbers. My A1, if we plug in these 4 numbers, so my A1 equals to, based on my calculation, that is C1 means cosine theta 1, and negative S1 means negative sine theta 1, and S1, C1, and 0, 0, and 0, 0, 1, and here I have the calculation that is A1, C3. Here I have A1, S1. Oh, sorry, this is C1. Okay, sorry, C1. And this is 0 because there should be D1. Okay, and here I have 0, 0, 0, 1. And my A2 equals to C2, S2, S2, negative C2, and 0, 0, and A2, S2, C2, okay, so here should be C2, and A2, S2. And this row is 0, 0, negative 1, because here we have the 180, and this is 0, because di is 0. And the last row is 0, 0, 0, 1. Okay, and my A3. Again, we plug in these 3 numbers. And there are 3 zeros, so this row is pretty easy to this matrix is pretty easy to calculate. So I have my calculation result as 1, 1, 1, and 0, 0, 0, 0, 0, 0 means my rotation, there's no rotation. And from the physical drawing, we can also see that there is no rotation between the frame 2 to frame 3. Okay, and there is only one translational motion on z-axis, so we have these 3 here, and here the last row is 0, 0, 0, 1. And how about A4? And A4, they have the same format, except here we have the cosine and cosine sine theta 4, so we have to do that. And so we have C4, which means cosine theta 4, and here we have negative sine theta 4, and here we have sine theta 4 and cosine theta 4. And here is 0, 0, and 1, and 0, 0, and here we have 0, 0, D4. Okay, so it means here we have a D4 and 0, 0, 0, 1. Okay, and the question is, finally, we want to calculate the homogeneous transformation matrix, which is in this case, we have the n-effectors frame is frame 4, so we want to know the n-effector in the real world coordinates, which is the frame 0, which is our base frame. Okay, so I want to calculate T40, so that is A1 multiply A2 multiply A3 and multiply A4, and if you use MATLAB, and you can quickly have this thing calculated. Okay, so if we do the calculation, and this is going to be our final result. Okay, and then think about now the next step is, once we have this matrix and we know this, again, this matrix means the n-effector in the real world space. Okay, and then we need to go to the inverse kinematics. Okay, so let me call it IK, means inverse kinematics. For the inverse kinematics, it means that we already gave the n-effector's position. So for example, in the video, we saw the industrial robotics, and it has to carefully control the n-effector's position, right? The position. For example, I want to move this sample from here to this location from another location. And these 2 locations are already known, and we need to accurately calculate these joint variables so that it can achieve those motion. Okay, so then it comes to the inverse kinematics. So we already know the task. The tasks means the final position, and we go back to calculate the joint variables. Okay, and now this is a 3D drawing, and this 3D drawing is clear, right? And imagine what we have seen from the video, and here we have a joint, and here we have another joint, and which is a revolute joint, and these 2, it can move around, right? These 2 joint variables, and these 2 revolute joints, they can move around, and then finally at here at the end part, we have a prismatic joint can move up and down, and right here we should have another revolute joint so that it can do a small rotation. Okay, and again, if we want to do inverse kinematics, the question is we assume that we know the final position, and means the final homogeneous transformation means this thing we turned out to be this T40. We know that as a real matrix. Okay, and this is R11, R12, R13, R14, and R21, R22, R23, and R24, and R31, R32, R33, and R34, and 0001. Okay, and this matrix is given because of the real tasks, okay? Because this thing, physically, it means the end effector in the world space. And say we have a ruler and we can accurately calculate and measure the task we want. Okay, and then the question is, we want to calculate these four joint variables so that we can achieve this homogeneous transformation, T40. Okay, and let me call it H because this is a real number matrix. And again, for the inverse kinematics question, in this case, we're calculating theta 1 and theta 1, and here we also calculate the second joint variable, which is theta 2, and we also calculate the D3 and theta 4. Okay, and also, what we want is a closed loop, closed form solution so that we can do real-time control. Okay, so finally, what we want is a rotation, means there is an alpha rotating from here, from the original x0 to the final position. Or final orientation. Okay, so this is our rotation matrix, and we want those because this is specifically for SCARA manipulator, because SCARA manipulator, we are doing a final rotation, and these three rotation axes are parallel. Okay, so then we use geometry method to do that. Actually, that is not very complicated for the SCARA. Okay, so what we do is, first of all, we assume that finally we achieve the orientation, and which is a alpha angle. And this final alpha means from this x0 to the final, maybe here we should have another theta 4, and this alpha means these, and here with this angle. Okay, if we do the projection to the x0 y0 plane, and here we have the theta 2. Okay, because theta 2 means the rotation from theta 2 means the rotation around the z1 axis. Okay, so here we have the z1 axis. Okay, and this is our, if we project it to the x0 and y0 plane, and this is over x1, and this is over x2. Okay, this is over x1, and this is over x2. Because we can see that here we have the link, and here we have the link if we project it to the x0, y0 plane, and that is clear. So actually for a SCARA manipulator, and that for the geometry method is even simpler than the previous oval manipulator, because first of all, we only have 4 joint variables, and also everything can be projected to the x0 and y0 plane, because all these rotation axes, they're parallel. Okay, so first of all, we know that these 3 rotation angles, theta 1 plus theta 2 minus the theta 4 equals to alpha. Okay, because alpha is the final angle we want to achieve. And because this is the final rotation, means the end effector's rotation in the real coordinates, in this real coordinates, right? Okay, and we have the final orientation of this tooling. So this can be calculated by the real number matrix, which is given right here, and we know that this is known, right? Okay, and so these alpha can actually calculate it by these two terms, because this is cosine alpha and this is sine alpha. Because this is cosine alpha and this is sine alpha, and this is R11 and this is R12, and these are real numbers. Because again, because these three theta, the rotating axes, they're parallel. Okay, so it means the alpha can be calculated by arctangent R11 and R12. Okay, and then we start to calculate these and all these joint variables. So again, if we want to use geometry method, we would like to see which angle is easier to calculate. And seems like this D3 is pretty simple, right? D3. Okay, so if we take a look at this drawing, and let me see if I have a clear one. Okay, so let me just use this drawing. Okay, from this drawing, we can see that what is D3? D3, okay, so we assume that we already know, because we know the homogeneous transformation matrix H is T40. Okay, so we know the thing as a real number. Okay, so it means that we already know the final position of the n effector, which is the desired position of the n effector. Okay, so these coordinates, the coordinates are corresponding to the R14 and R24 and R34. Okay, so then we can quickly calculate our D3, because D3 actually equals to, from the drawing we can see that D3 equals to OZ plus D4. Okay, and what is OZ? And remember that the homogeneous transformation matrix, we have H equals to RO01, okay, and this O, RO, and this O actually is a vector that is OX, OY, and OZ. It means the n effector in the world space, right? In the world space, which is our final goal, okay? So it means the final position of OZ is known, so we can quickly calculate D3. D3 equals to OZ plus D4. Okay, and then let's see which one is next that could be calculated. And how about theta 2? Okay, so if we want to calculate theta 2, and theta 2 add this angle equals to pi. Okay, so it means if we want to say, I call this angle as beta, and if we want to calculate beta, and in this triangle, and the good thing is we know if we project it to the x0, y0 plane, and this equals to this length, and this one equals to this length, because there is no up and down, and we cannot really do the rotation in this, we cannot do that, right? So it means these are actually all parallel, and this is horizontal and this is horizontal. So although it should be horizontal, okay? Think about the video we have seen, okay? So this is horizontal. Okay, so it means this length directly equals to the length, and this length directly equals to the length. Okay, so now from this triangle, we know this is A1, and this is A2, and this length is calculated from this triangle. Okay, so again, if we draw the top view of x0 and y0, and then we have, this is our final position, and here we have our OX. Okay, so because this point is this point, right? And so here we have over OX, which is corresponding to the final position of the end effector, and this is OX and this is OY. Okay. And again, projected to the x0, y0 plane, here we have A1 and here we have A2. Okay, and seems like we can quickly calculate cosine beta. Cosine beta equals to A1 square plus A2 square minus this R square over 2 times A1, A2. Okay, using the cosine rule. Okay, and our R square equals to OX square plus OY square, and again they are the real numbers that you can read from this H matrix, which is the real number matrix, and so we can quickly calculate cosine theta 2 equals to negative, because theta 2 plus beta equals to pi, so theta 2 equals to negative cosine beta, and that is, I plug in the R square. So I have OX square plus OY square minus A1 square minus A2 square over 2A1, A2. Okay, so it means we directly calculate theta 2, and that is great. And how about theta 1? Okay, so seems like we can calculate theta 1 as well. Okay, and theta 1, if we want to calculate it, theta 1, okay, theta 1 equals to this angle, and I'd like to call it, let me call it gamma, and this angle, let me call it phi. So theta 1 equals to gamma minus phi. And what is gamma? Gamma is pretty quickly calculated. We can quickly calculate the gamma, which is this angle, so that is arctangent OX, OY. Okay, OX, OY. And how about phi? If we want to calculate phi, and we need to take a look at this triangle, and we're able to calculate it. So it means that we need to use here, say we do a calculation, and the phi, this R equals to the A1 times cosine phi plus A2 times the cosine pi minus phi minus beta. So this triangle, we're able to calculate this phi directly. And I will skip the calculating procedure. So here I directly write down my calculation, which is this phi, and that is A1 plus arctangent A1 plus A2 times cosine theta 2 and A2 times cosine theta 2, okay? Sine theta 2, sorry. So I write as S2, okay? So here again, C2 means cosine theta 2 and S2 means sine theta 2. Okay, so now we have the 3, and we have theta 2, and we have theta 1, and the last one is theta 4. Okay, and how about theta 4? And theta 4 is here, right? So that is theta 1 plus theta 2 minus alpha. And theta 1 is this thing. And theta 2 is this thing. Okay? And alpha is the thing. So we can calculate these 3 angles so that we're able to calculate theta 4. Okay, so that's it. So we can see that from the geometry method, and we read the triangles, and we, from the final homogeneous transformation matrix which is given, and we can read the final end effector's position and orientation, and we can go back to use the geometry to solve it. Okay, so here we list these calculation. Okay, So now for the inverse kinematics, as a quick summary, is that normally in the real example, if we want to do the analysis of a manipulator, and normally we start from the forward kinematics analysis using the DH convention. And then after we have the final T and 0, and then we can, for inverse kinematics, normally we give this T and 0 equals to a real number matrix so that we can solve for all the joint variables, okay? And if we want to solve that from inverse kinematics, and we need to go back to take a look at the geometry, and then we do the calculation, okay? And actually, based on our class, I want to tell that if you cannot really do the detailed analysis of geometry, analysis is fine. So what I want you to remember is you can directly remember the SCARA manipulator, because normally if you see a robotics in industrial manipulation, and we deal with the SCARA manipulator, and that is the first example, and just remember that. So it means you don't need to do the calculation yourself, and just remember these joint variables. Okay, and the second thing you need to remember is this elbow manipulator. And for this elbow manipulator, and this is a manipulator base plus a spherical wrist. This is the spherical wrist, and this is the manipulator base. Okay, so if it is not for the, here is a Puma robot, right? It's a Puma robot. It means it is an elbow manipulator. And if it is not a elbow manipulator, and say if it is other type of manipulator base, say RRP, and you can also go back to our example and see what are the joint variables we calculated. Okay, so what I want to say here is that, okay, so I want you to get the idea of geometry method to calculate the two cases. One is that the manipulator with a spherical wrist like this one, okay? And the second one is like the SCARA manipulator, that is a manipulator without a spherical wrist. And so first of all, I want you to get the idea of geometry analysis. Just read it and see the projection and read all the length and use the geometry to solve it. And then if it is too complicated, and think about these examples we have shown, okay, and remember these results. And probably if you see a manipulator in the future, it's probably going to be one of these examples. Okay, so it means you can directly go to the slide and use those joint variables closed form solutions directly. Okay, so I will stop here for today.